It gets more complicated once you have substituted cycloalkanes. So now we have methyl cyclohexane. So now let's draw methyl cyclohexane. I've got one methyl group and it's going up. Now you can pick any carbon in the whole molecule. It doesn't matter where you pick to draw it going up. Usually I pick one of the ends. I'm right-handed, so I like picking the right end, but it doesn't really matter where you pick. I'm just going to pick a position. I'll use this red one. And I'll say at that position, I'm going to add that methyl group. My methyl group is going up, so the up position here is an axial. So that's my methyl group, up and axial. However, if I had chosen a different position, the up would be equatorial. And so that kind of leads into the idea of ring flips. And you can see this if you play with models as well. But if I grab this end and pull it down, and grab this end and push up, I can, with just the rotation around sigma bonds, single bonds, I can change to the opposite chair structure. So now this end is at the top, and this end here is down at the bottom. So now that I've inverted that, what happens is anything that's axial in a ring flip becomes equatorial. Anything that's equatorial in a ring flip becomes axial. So this group, as I flip it over, turns out that it's going up this way. Now it's up and equatorial. Back here, it was up axial. Now the next thing that we want to figure out with this is about stability. Which one is better? Is it better to have this group axial or have it equatorial? And it turns out that there's problems with axials between the 1 and 3 positions. So if this is 1, 2, 3 that direction, or 1, 2, 3 this direction. And so you have these bad interactions between things that are 1 to 3 apart, because those are all the axials facing the same direction. There's no problem with the axial at 2, because that's going opposite direction. So we call this 1-3 diaxial strain. It doesn't exist in an equatorial. Because if I look over here, this is my one equatorial on this side is going up. The equatorial on this side is actually going down away from that one. So they're not in the same space at all. So 1-3 diaxial strain is going to cause things to not want to be in the axial position. So now I have to choose between the two of these. So I've either got axial methyl cyclohexane, or I've got an equatorial methyl cyclohexane. And it turns out that this one is lower energy. It's really all about sterics again. It's about large things not wanting to be near each other. And it's not favored a lot. It's favored by 1.74 kilocalories per mole, which is about 19 to 1, or about 95%. So it's enough that this will try to stay equatorial as much as possible. But you'll have some of them that will be in axial position. Now what happens if I put a larger group on there? So now this is a T-butyl group instead of a methyl. A methyl is a carbon with 3 hydrogens around it. Now I've got a carbon, and each carbon has a CH3 around it, so it's much, much bigger. So now my 1-3 diaxial strain is even greater. So if I have to choose between the two, I can ring flip. Again, here I have the axial. Here I have the equatorial. And now the equatorial is favored about 4,000 to 1, which is from 4.9 kilocalories per mole. Energy difference between those two. So in this case, we would say that we have nearly all of the equatorial one. The other one was only 19 to 1. We have quite a few of the axial ones around. Once we get a large group like T-butyl, it's practically all in the equatorial and almost none left in the axial. Right? What happens if we have 2 groups on there? All right, now I put 2 groups on. The first one is up, the second one is down. So again, just pick a position somewhere on the molecule, and I'll pick here to start and say that that one's up. And then next to it, to the right of that one position, so to the right one position here, I've got another methyl group, and that's going down. So I can look at this now and say this one's axial, and this one's axial. So do you think this is going to be the lowest energy conformer or the highest energy conformer? Hopefully you could already figure out that that would be high. If I do a ring flip now, this one that was axial before becomes equatorial. And this one that was axial before becomes equatorial also. So now I've got axial, axial, equatorial, equatorial, and then this would be the lowest energy one with both of them equatorial. Let's do one more example. In this one, I'll ask you to try and pause the video and try to do this one completely on your own first, and then come back and check the answers and how it worked. This is a different stereochemistry of my dimethyl. They're both going up for dimethyl cyclohexane, 1,2-dimethyl cyclohexane. Both of them are going up. Try and draw one of the chair conformers, then do a ring flip on that, and try to draw the other one, then figure out if either one of them is lower energy or if they're the same. All right, so these are both going up. So if I pick my spot, I always usually pick the same spot, methyl going up, and I'll pick the spot to the right of that, the methyl is going up. So both of them are going up. This first one's axial, the second one's equatorial. Now if I do a ring flip, the one that was axial before is now equatorial. The one that was equatorial before is now axial. So here I have one axial, one equatorial. Here I have one axial, one equatorial. And since they're both the same group, both of them are methyl, neither one of them is larger than the other, their energies are actually equal. So neither one of these two is favored because in the end they're the same structure.